Welcome everyone to the 8th hydrogen session. And today we're going to explore a topic which stretches my expertise a little bit, but I think this is an area that is critical for us to all begin to get an understanding of, which is the emissions associated with current hydrogen production are extraordinary. They're huge. They represent 2%. Actually, depending on how you calculate it, maybe even close to 3% of global carbon emissions are due to current hydrogen production. And that's significant. We hear about concrete industry, we hear about other industries, but hydrogen is in the mix as being a significant contributor to global carbon emissions. And we also hear quite a bit about the use of what's being called direct air capture, or DAC, in terms of putting up machines to capture carbon out of the atmosphere. That's a really long range activity. The amount of carbon that is in the atmosphere is very small in terms of concentration, which makes it very expensive to remove carbon from the atmosphere. But when you have a gas stream with 40–45% CO2 or even richer levels, the cost to remove that carbon from that stream are a lot less. And SMR, steam methane reforming, which is the dominant approach to generating hydrogen today around the world, has a fairly high concentration of CO2, which makes it a great candidate for removing carbon. And I think we'll see quite a bit of this going forward. And I think we'll see several strategies, but one is to replace steam methane reforming with electrolysis, and the other is the post-combustion CO2 removal. So let me bring up the presentation for today. Okay. So today we're going to talk about producing hydrogen with carbon capture, use, and sequestration. And we see this term, carbon capture, use, and sequestration, in several different forms. CCS is a very common way to describe it, which is carbon capture and storage, or carbon capture and sequestration. And the word use has been added in over the years to illustrate that there are uses for CO2 that we can apply the carbon that's been captured. Today's webinar is put on by the Hydrogen Energy Center, which is phenomenal in its prescience, being formed 25 years ago to facilitate a renewable energy future with the use of hydrogen as an enabling technology and solution. We're certainly seeing in this most recent period that the world is catching up to this view of hydrogen as an enabling technology. HEC has primarily been focused on providing information to the public and to various legislators and public officials about the role of hydrogen in the renewable energy future. We have also been involved in various studies of market opportunities for hydrogen with the Connecticut Center for Advanced Technology. And the Hydrogen Energy Center also, about 15 years ago, implemented a phenomenal project, which was a hydrogen generation using solar power, storing that solar generated hydrogen on site, and then regenerating electricity using electrolyzers. And this facility was built for an animal shelter at an organization called the Chewonki Institute in Maine. And it was designed to provide backup power for a 3-day period for animals that were being recuperated. And the thing that was so prescient about it is it was completely carbon free. It was all on site, and it was long duration storage as well. And that's a key role that we're seeing emerge in hydrogen today. The upcoming hydrogen session, we have a session on wind to hydrogen, which is a key driver of low-cost electrolytic hydrogen, pretty much led by companies developing large offshore wind farms in Europe and landing those wind farm energies on the northern coast of Germany and in Denmark and Great Britain, and converting the excess wind energy to hydrogen and injecting that hydrogen in natural gas pipelines, or using it in steel manufacturing and other industrial processes. Valerity is also a sponsor of today's hydrogen session, and we're involved in the area of renewable natural gas and hydrogen, are involved in projects principally with gas and oil companies that are exploring ways to mitigate carbon emissions using these lower carbon solutions, or looking for growth strategies to participate in the energy transition underway. So we've all heard of the colors of hydrogen. And there are some people, I mean, I've heard that nuclear power now has 2 different colors. One was gold that I heard recently, and the other was pink. And I don't know which way the nuclear industry is going with their color choice, but let's put that aside for the moment and look at what all the hydrogen pathways are. And this is a fundamental element of moving to a hydrogen economy as was envisioned in the 1960s, is that hydrogen represents, I think, 76% of all the material in the universe. It's a ubiquitous element. And in that way, there are many ways to get access to hydrogen. Now, there is a company in Canada that claims to want to mine hydrogen from the earth. But for the most part, hydrogen does not occur naturally. You have to separate it from something else. So on the left side of this chart, you can see that first step of this separation idea is electrolysis, where you separate water to produce hydrogen. And you can use renewable energy or nuclear power. Of course, you can use any electricity from the grid. And that indeed is what we see on the right side of the chart, which is electricity from the grid. So on the left is the green hydrogen pathway. And on the right side of the chart is the, I don't know what color that is. Maybe there's not a color for normal electrolysis off the grid. Maybe our opportunity today is to invent a new color scheme. Next is the gray hydrogen, so-called, which is the normal way that hydrogen is produced, and that's the bulk of our discussion today, is taking gray hydrogen and turning it into the box next to it, which is blue hydrogen. So you can take hydrogen from natural gas, steam, methane reforming, and capture the CO2, and then you can claim it as blue hydrogen. And this is an important part of the hydrogen strategies going forward. And coal is not much used for hydrogen production in the United States. It's important to recognize it because it's a major contributor to hydrogen production in China, and a major source of hydrogen in China, and it has very significant climate implications. And so let's hope that China is pursuing some of these strategies to mitigate the emissions associated with coal-generated hydrogen as well. And I do want to mention that we do have Q&A at the end of the presentation, plenty of time for that today. And so please use the chat box to put in any questions you might have throughout the entire presentation, and we'll address those at the end. So you can see that there are different levels of carbon emissions associated with the hydrogen pathway. Coal gasification, you can see that, just to let you know, this is an interesting way to express it, but it is helpful. It's the kilograms of carbon dioxide per kilogram of hydrogen produced. And so you can see that coal is about 18 kilograms of carbon dioxide are produced for each kilogram of hydrogen that is produced. Next in the order of carbonation into the atmosphere is steam methane reformation, SMR. And this figure of 10, we have a figure in some of the work in this presentation of about 9, but it's in that range. It's 9 to 10 kilograms of CO2 per kilogram of hydrogen produced. And then there are some additional information here. You can see the color coding has been continued. Coal with 90% capture, gas with 56% capture, gas with 90% capture. Now, why do we have different capture rates? Well, it depends on the technology that you're using to capture the carbon. There are different approaches that can be taken that all have different cost implications and different carbon impacts, and we'll see that. And then, of course, we can see on the far right of this chart, the lowest carbon. And to be truthful, there is carbon that's released when you build things and when you take things apart at the end of their life. So a more thorough analysis would include those carbon impacts, but for the most part, they're fairly small. So again, we're kind of looking at the marginal carbon impacts of producing hydrogen. Now, electrolysis itself has a wide variety of emissions associated with it, depending on the source. It is very interesting to see, for example, that when hydrogen is used for transportation, for the most part, it definitely appears that there's a real emphasis to make sure that the hydrogen is clean. It's a little obscure, but the Department of Energy recently issued a hydrogen shot, or they have this shot nomenclature, and the hydrogen shot is to get to $1 per kilogram before the end of the decade in terms of being able to produce clean hydrogen. And when they say clean hydrogen, I think it includes not only green hydrogen, but maybe blue hydrogen as well. So there's a little squishiness on the definition. So it's a clean hydrogen, which may not be all the way to green. And this is illustrative of that if you use different sources of electrons, you're certainly going to have different levels of carbon dioxide emissions. In California, for example, when you run one of the 10,000 hydrogen cars that are now currently operating in California, the hydrogen actually comes from natural gas. So it's the figure here. Potentially, if you use electrolysis, but it actually is SMR hydrogen of about 10 kilograms per kilogram of hydrogen, and they buy offsets in order to green up the hydrogen from the biofuel industry, and that's the strategy in California. Here in the Northeast, I understand that the strategy is to buy liquid hydrogen for transportation and to buy it from Hydro-Quebec generated hydrogen through electrolysis and hydropower, and that is fairly clean. Now, I also understand that that might be a mix, that it may not be 100% green hydrogen, depending on the source of electricity, but it all bears closer scrutiny so that any claims that are made are accurate in their representation. The global hydrogen market, and here's another use of words that is very specific, which is the global pure hydrogen market. It's a little twist here. There's quite a bit of hydrogen that's produced that is used in mixed gas circumstances. And that's used in industry where cleaning up the hydrogen is not needed. They need to use the gas mix for some other process. So it's okay not to generate pure clean hydrogen. In this particular case, we're looking at, this represents about 60% maybe of the overall hydrogen market, but this is the pure hydrogen portion of the market. And this is the sort of the more meaningful to today's discussion, certainly. A couple things to notice. First of all, most hydrogen is used for refining and ammonia, and methanol is in this mix as well, methanol production. And then there are other uses for hydrogen. So greening up of ammonia is a key strategy that's being pursued in different parts of the world, as well as the refining. The other that is surprising to me, of course, is that the growth in the generation of hydrogen in the global market is extraordinary. I mean, it is doubled in the last 30 years, it appears. And so it's quite a bit of growth. And so the question is this industrial use of hydrogen going to continue? And if we reach peak oil, I assume that we'll see some refining intensity of hydrogen use level out, if not decline. And then we can see the greening up of ammonia is very aggressively being pursued around the world. So we'll begin to see the use of gray hydrogen presumably begin to go down, not just because we're cleaning it up, but also because the root demand might be shifting. Most of that hydrogen is produced from steam methane reformation. And these are the numbers that are associated with how much carbon is released when we do steam methane reformation. And you can see that number I spoke about earlier at the bottom, just over 9. And this is based on an analytical work that is indeed very accurate. And in practice, it's seen that the number is a little bit closer to 10 if you go for the actual measurement. And there's certain efficiencies in the process that reduce or impact negatively the carbon emissions quotient of steam methane reformation. And there are a lot of processes in steam methane reformation, and it's basically energy that's driving the overall process. And then, of course, the major contributor, the next to last line, the 6.26, that's the carbon dioxide that comes out of the natural gas and water. That's the methane contribution to the carbon dioxide emissions. And what's the point of having these factors? We can actually apply the factor for steam methane reformation carbon emissions to the actual size of the hydrogen industry. And we can see indeed that based on this calculation, that we're up at about 2.1% of global emissions are due to hydrogen generation from steam methane reformation. If we're to achieve the carbon objectives, it's like climbing up a mountain on one day, and then the next day you have to climb down the mountain. And that indeed is what some would hope this chart would look like that it would hit a peak and begin to go the other way. I apologize for having such a simplistic chart, but I think it's important to have some framework to understand what we're talking about when we speak about carbon capture, use, and sequestration. On the top left side is the carbon capture side. So you can see the illustration of a smokestack, and indeed we're capturing the carbon off of that system somehow. There are also, you can see two little fans below the smokestack diagram, and that would be the DAC, or direct air capture methodology. And again, I recently heard a talk about direct air capture, that one of the companies that's pursuing it, the cost per ton of carbon captured in this process is around $1,100 per ton. And the current carbon pricing is around $50 a ton. So there's quite a distance to go between $1,100 and $50. And so direct air capture may be good in theory, and maybe we have to begin developing technologies that get us to 20 years from now, but it really is not a near-term approach. And in fact, one of the early industry leaders in understanding the carbon capture technologies was asked, this is kind of hilarious, was asked if they would invest in a direct air capture company, of which there are several, and clearly demurred on that opportunity. The second thing is, and this is huge, what do you do with the CO2 once you've captured it? And there are a couple things going on. First of all, if you're near a petrochemical base or industry core, if you're in the Texas Louisiana belt, or if you're in the near the North Sea, Scotland in Great Britain, you have the opportunity to take that carbon dioxide and transport it via pipeline and inject it into depleted wells. You also, however, and this is kind of maybe absurd in some view, but the biggest market for carbon dioxide is oil recovery, and the or enhanced oil recovery, EOR. And that's where you inject CO2 into wells, and you actually, that CO2, the pressure from the CO2 helps release oil and get additional resource out of the ground that are basically somewhat depleted wells. And so enhanced oil recovery is a way to get more oil out of wells that are not as productive. And some of that CO2 doesn't stay in the ground. And so it's not the greatest method, but it is a market that uses CO2. The other approach, which is being used in Canada and Europe and other locations, which is to identify depleted wells and inject that carbon dioxide into those depleted wells. And that, Japan pursued deep ocean, putting carbon dioxide in the deep ocean, and somehow it was going to stay down there. That approach is not being pursued anymore. And apparently, just so everyone knows, there is an extraordinary amount of volume of depleted wells available to store carbon dioxide. So it's not a resource constraint in terms of depleted wells. But the key resource constraint is, how do you get the carbon from where you capture it to the well that you're going to inject it? And that means that a lot of what goes on in terms of where we emit carbon is not located in a spot favorable for enhanced oil recovery or depleted well injection. And that's a key point. Now, there is a fairly significant pipeline in the middle of this country for CO2. So I think we will see, I think it might be a 1,600-mile CO2 pipeline. I think we will see CO2 pipelines expand as we move forward in order to do the reverse trip, to capture the CO2 where we can and to transport it where it can be injected in depleted wells. There is a function for using captured CO2, and in fact, there is a facility being built in Portugal to turn CO2 into a synthetic liquid fuel for air travel and for vehicle transportation fuel. And the sort of the synthetic liquid fuel industry is looking at using CO2 and generating hydrogen from renewable energy and creating synthetic fuels as well. Now, what is the process for this thing we call capture? Well, the way it's done is you take CO2 and you find a material that is a scavenger material that will absorb the CO2, and then you have a process where you change the conditions, temperature and pressure, and regenerate the absorbent material and eject the CO2. So it's a absorb it from a mixed gas and then regenerate it in a non-mixed gas situation, so it's a higher concentration of CO2. And so, we really don't need to go over all the details of this particular chart, but it's fairly straightforward. You can see the main column on the left is called the absorber, and the main column on the right is called the regenerator. And basically, amines are used in a circular fashion to absorb the CO2. And you can see off the absorber, there's a sweet gas escape. And on the regenerator is where the CO2 rich gas is ejected. And a lot of these cases, the amines are used also to absorb hydrogen sulfide, which is not a very good element to have when you don't want to have corrosive activity on metal parts within petrochemical plants. So amines are used not just for CO2, but also hydrogen sulfide removal, depending on what you're dealing with and the proportions. So this is a fairly known standard approach that's used for capturing carbon. And this is what pretty much everyone does and is planning to do on a post-combustion carbon capture situation. The amines are, there's a range of them, so it's not just one that's used. And the major ones, as I understand it, are the MEAs and the MDEAs that are used in these processes. And again, you can see that there are different levels that are used depending on what you're trying to achieve. And I think the one thing we haven't addressed in this presentation as yet is that when we touched on it earlier with the atmospheric direct air capture of carbon, is that there are different concentrations of carbon in different processes. And SMR has one of the highest concentrations of carbon in its flue gases, and it makes it a lot easier to separate the carbon. Coal, for example, I think is the worst. I think they only have 15% CO2 in the flue gas. And so various processes have different levels of carbon. So you apply different carbon methodologies, carbon capture methodologies depending on what that slipstream is that you're trying to address. And so it's not a one size standard fits all kind of solution. There really is a diversity of gas mixes that are out there that need to be addressed. In simplified form, a steam methane reformation system consists, as you see, natural gas and water coming in. There may be other materials, but those are the dominant ones. And you first go into a step of steam reforming, which is a nickel catalyst in tubes at high temperature and pressure. And in that case, the CH4, the methane, breaks apart, and the H2O also, and you end up with a mix of gases, including carbon monoxide, CO, hydrogen, and CO2. And then you go through a water gas shift process in order to pick up additional hydrogen and form additional CO2, get rid of the CO. And then in the final step with all the mixed gas, you have pressure swing absorption, which is the cleanup step, where the gas enters the chamber at a certain pressure and temperature. You then separate that chamber from the rest of the process, reduce the pressure, and certain gases come out first. And that's the separation part of the pressure swing absorption process. So you get hydrogen coming out, as well as a tail gas with the other elements dominated by CO2. And that can go into the feedstock pretreatment, which is basically a combustion chamber. And the little numbers in blue, there's 1, 2, and 3 on this chart. Those are the places where you can put in systems to reduce carbon on an SMR system. The biggest one is 3. I mean, that's the dominant one. I mean, you put your amine absorption system on the flue gas, and that's where you can get your dominant reduction. But you can also do it in these other steps, which are contributory to reducing carbon dioxide, but don't do the lion's share. So just to be clear, I earlier spoke about there are different approaches that can be taken, each with different levels of carbon mitigation, as well as different economic considerations. So this is an analysis of some approaches that can be taken. And it's a little bit of a detail, but it shows the fundamentals behind what we're talking about. And just in the simplest form, just to focus on the chart first, without going into the cases that are modeled. Well, we'll talk about each of the cases, but to begin with, the red dot on the far left side of this chart, the one that has the number $1.52, that's basically the cost to produce hydrogen from steam methane reformation without any carbon capture. So the axes here are CO2 reduction on the bottom axis and hydrogen cost on the vertical axis. And you can see that as you reduce CO2, the cost goes up. It's a fairly linear expression of cost and reduction. So the base case, $1.52, pretty standard price. If you do steam methane reformation, the hydrogen cost anywhere from $1.20 to $1.80, depending on the particular location, the cost of gas. Right now in Germany, I think the cost of natural gas is about $9 per MMBTU. If we're getting gas off the Marcellus shale system in Pennsylvania, here it's about $2.60. So you can see why there would be a wide range around the world of the cost of steam methane reformation to hydrogen, because the cost of the feedstock, natural gas, varies significantly around the world. The furthest to the right dot, the sort of the yellow tan colored dot that has $2.20. That's the 90, that's the king of the hill or the queen of the hill. That's the 90% reduction in carbon emissions with SMR. And that gets you up to $2.20. So you can see, that's about getting close to a 50%. Let's just be absolutely clear. That's getting close to a 50% increase in the cost of hydrogen when you put carbon capture on steam methane reformation. Not too bad in the grand scheme of things, but just to be clear, that's what it does. The other approaches are a variety of means, as I mentioned, that are inserting carbon capture systems at different steps in the steam methane reformation, each clearly with different cost implications and different CO2 reduction implications. Another version that looks at these numbers as well, this is a little bit more in terms of geography around the world, and sort of broadly with no carbon capture use and sequestration, or with carbon capture use and sequestration. And you can see that it varies around the world, and that there indeed is about a 50% increase for the most part. Some of the places that start with a high natural gas cost, their premium isn't as high from a percentage point of view, because the stepwise function in carbon capture is really due to the increased cost of the equipment and the increased amount of energy that you're using in the process itself. And so that is not a proportional increase, that's a fixed increase depending on what your starting point is for the most part. And you can see that illustrated here. Now, I have a few slides here that I do want to present, that there are, when you look at carbon capture, you can have post-combustion carbon capture, which is what we've been talking about, but you can also have pre-combustion. And there's an approach called oxygenation, which I'm not presenting today because it is still somewhat in the development stage. It's using combustion processes with pure oxygen, not introducing nitrogen. And there's some implications there, but I haven't seen it in practice, and I may be surprised if somebody speaks up as well on that. I'm willing to learn. But this is an amazing process that's being pursued. It's being pursued at MIT. It's being pursued at universities around the world. It's being pursued in a big way by Mitsubishi, which has invested in this process, and it's called methane pyrolysis, if you ever want to look it up. And methane pyrolysis is where you take methane, CH4, and you put it through a very high temperature, and what happens is the methane is, the elements are separated out through the high temperature. And it forms what's called elemental carbon, sometimes called molecular carbon. Basically, it forms a very fine carbon dust that precipitates out of the process, no CO2. And so this is a fascinating process where theoretically you could have a power plant that runs a turbine today, and instead of running it on natural gas, you could put in methane pyrolysis at the final step where the natural gas arrives at the plant facility, and you could precipitate out the carbon in solid form, which makes it a lot easier to dispose of or use. It is carbon black, which is used in tire manufacturing and other industries, but it's a lot easier to deal with than CO2, a gas. And then you could feed the hydrogen directly into the turbines. Turbines today can take upwards of 20 to 30% of hydrogen in a gas mix, depending on the design. And there are expectations that by 2026 or so, we'll be able to run 100% hydrogen, or the first turbines will be introduced on a development perspective that might meet some of the emissions criteria, so they could be considered for 100% hydrogen as well. A lot more details on that, but not for today's session. So the idea being that if you could do this method of carbon separation on a pre-combustion basis, it might be a breakthrough. One of the challenges, however, which is really the core of all the research on methane pyrolysis, is that when the carbon precipitates out in the combustion chamber or the heat chamber, it affixes itself to all the chamber walls, and it's really hard to handle. It basically clogs up the system. And so somehow Monolith Materials in Nebraska has figured out a process that they can address this accumulation of carbon, which is so problematic in the process. And then a company called C0 is pursuing it in Santa Barbara. At MIT, they're using molten tin at a very high temperature, which the pyrolysis takes place within molten tin. And it makes it easier to flow the carbon away from the process through the molten tin, and then to have another separation of the carbon that presumably would precipitate up out of the tin as well. The hydrogen gas in a molten tin bed would certainly just, move up in the gaseous phase out of the liquid. And so that's pretty clear, but I look forward to hearing how they separate the carbon from the molten tin in this new kind of design. These are some of the companies that are pursuing, some of the big companies around the world that are pursuing this technology. And I think we'll see a lot more of this type of solution develop going forward. And this is just to show Monolith Materials has actually built a facility and they've been operating it for 5 years. It's designed to produce carbon black. They didn't design it to make hydrogen, and they're building a complementary plant next door to produce ammonia now that they have all this hydrogen. So they're not trying to feed the hydrogen into any kind of energy production or hydrogen market. They're now figuring out that they're going to put in an ammonia plant to use the excess hydrogen from the process that was designed to produce carbon black. And then C0, same thing, fairly sizable process to precipitate out the solid carbon with the pyrolytic process involved in as well. So the remainder of this presentation, I'm just going to zoom through because I can see we should be opening to questions soon. And these presentation materials are going to be available for you after the presentation. We'll post them on the Hydrogen Energy Center site for you. So I am going to take the opportunity to rush through a few of these, but just to show that the industry has really moved ahead in terms of addressing some of these issues. This was a facility that was built for enhanced oil recovery. So it's in Texas, and it was put in operation, as you can see, in 2013. And the CO2 was then used for enhanced oil recovery. So that was the purpose in doing the carbon separation here, not to reduce carbon emissions. Japan is moving ahead. They're very aggressive with addressing carbon issues. And this is a plant to inject hydrogen for testing and evaluating this methodology to sequester CO2, excuse me. I've spoken about this project in an earlier because this is a large SMR as part of the petroleum industry in Canada that takes tar sands and produces oil products. And in the production of oil products, as we've mentioned, you need to take sulfur out and do other things, and hydrogen is used for that. So they have several, I think 3 very large steam methane reformers. And they've also just started stripping off some of that hydrogen to be used for injecting in a natural gas pipeline. But the key here is that they're taking that CO2 and pumping it into a depleted well. And they are making every effort to decarbonize as much as possible to enable the continuation of their petroleum business. So it's kind of an interesting, I think they've invested over $1 billion in this facility. This is certainly another project in the United Kingdom. And again, it has to do with sort of the classic case of injection. I want to get to some of the other projects here, and then we can open up for questions. This is a supply chain from Australia. Australia, similar to Canada, has a very strong interest in maintaining, they are one of the largest exporters of coal in the world. And they also export natural gas. And they want to keep that business going. So there's a strong effort to decarbonize it as much as possible. But they're looking at using coal to produce hydrogen and then to ship that hydrogen to Japan and to complement that project with carbon capture and sequestration as well. Now, I did just want to mention this one, and we're going to see a lot more of this going forward, and then I think we'll open for questions. But the concept of carbon negative carbon negative is a process where you use a biomass to produce energy, but then you capture the carbon that's emitted from the biomass combustion, and you sequester that carbon. And this is one of those potential systems because it's seen that if you're using a regenerative biomass resource like trees, that those trees will be regenerated and capture carbon going forward. People are concerned about biomass because you may be emitting a lot of carbon today, but then capturing it over decades. And so there's a mismatch of the timing issue with carbon sources and sinks. But the point being is that if you capture the carbon on a regenerative biomass resource, and the regenerative element of the biomass continues to absorb carbon, that your net effect on the carbon model is negative. And so we are seeing more of that, that if you capture carbon off a biomass resource, it can be claimed as a negative carbon facility, which is very interesting. And then a few other, this is one of the major projects for using hydrogen in pipelines and generating that hydrogen from both electrolysis as well as steam methane reformation, and then injecting the carbon dioxide into offshore depleted oil wells as well. And so there are several others that can be investigated as well. So with that, I would like to open this up for question and answer. And Rick, your assistance on this would be fabulous today.
Well, Brad, I'm going to start with a question that's on pyrolysis. Someone's asked whether the process is, I've lost the Q&A, where'd it go here? Whether the process is endothermic, and someone else has said that thermodynamically it's more favorable than water splitting. Do you have any comments on the amount of heat that it takes to do this process and where that heat comes from?
Yeah, I mean, that's the key. I mean, one of the, uh, when you saw the carbon capture numbers and you want to do, if you want to do 90% carbon capture with amines on the natural gas steam methane reformation, we're talking about a 15% increase in cost. And that's really due to a 50% increase in energy. I mean, it just uses a lot of energy. And that's really what all these processes tie back to. And it bears looking into, because the field is so new, it bears looking into what that is. But the temperatures are very high. I think they're upwards of 1800 degrees C, 1900 degrees C. And so it's not, it's endothermic, if I have the terminology correct. It takes energy to do that process. That's it. I mean, that's it. The process of gasification using pyrolysis, it's a one-step high temperature thermal process with a big energy input. And that's the key to the process. You can then separate the gases and use the waste stream as a form of heat as well. So that helps. But it is endothermic, if I have the terminology correct. It takes energy.
So there's a general question from Kyle Rooney. Do you see the target of $1 per kilogram of so-called clean hydrogen to be a reachable goal by 2030 from our point of view? What do you envision as the rate by 2030? I have a comment on that, but I'd like you to go first, Brad.
Yeah, I think we should all play with crystal balls, because I think, envisioning the future is something, we love to do. I don't mean to be specious, but it's very difficult to draw predictions. But let's just talk about what we know. You can produce hydrogen for $1 a kilogram using electrolysis today. So it really is creating a new geopolitical realm. And that new geopolitical realm is, we've had a presentation that talked about the global trade in hydrogen, and we looked at the formation of what are called hydrogen hubs. And these hydrogen hubs, if you're going to build a hydrogen hub, if you have investment dollars and you want to enter that business, the criteria is find a desert next to an ocean. And any desert that's next to an ocean, they're going to be very powerful in the coming decades in terms of energy, because they'll be able to deploy very large solar facilities that generate hydrogen at an insanely low cost. We're already seeing $1 a kWh. I apologize, I mentioned this on a lot of our discussions because it is a key underlying factor. It's the real driver behind this new hydrogen epic. That if in India and in Saudi Arabia, there recently were $1 per kWh PPAs. And these PPAs mean you can produce hydrogen for 50 cents a kilogram on a marginal cost basis. Now, being on a desert on an ocean means you have to get it somewhere and put it in a different form. I mean, there's a lot of costs that stack up. So it's very tricky to sort of say. I mean, it's going to be a very geopolitical realm, and we're already going to see very low hydrogen costs in different locations around the world. But that's not really useful. What's more useful is trying to get it to where we need it and can use it, and that's the key. So it's a combination of things. It's the cost to get the hydrogen, it's the cost to put it in a form that you can transport it, the cost to transport it, and then the cost to convert it back into a usable form. And it's kind of a lot of uncertainty. It's not like natural gas, where it's a ubiquitous commodity of a certain price, and then maybe some sort of price premium depending on where you are in the country. Europe, they are planning the gas companies got together and put together a plan for building out 25,000 miles of hydrogen pipeline. And just to be clear, most of it would be converted natural gas pipelines. So fairly significant. So if you have a port of entry, I think it's Rotterdam, is one of the major investors and partners in hydrogen production around the world. Right now, Rotterdam apparently handles about 20% of the energy used in Europe. They want to have the same role in hydrogen as they go forward. They're going to see their decline in the fossil-based side of their business, and they want to make sure they're well positioned. So they have positions in Qatar and Saudi Arabia and Australia as partners in order to acquire hydrogen resources to come through the port of Rotterdam. So it's going to be fascinating to see this bulk hydrogen market and distribution take off, because that's how you're going to begin to see some leveling of the price availability. And again, that's going to be the key. I'm sure I haven't answered the question, but I've done the best I can so far. Rick, do you have a perspective?
Yeah, I have a few comments on this. The first, to underscore the importance of what Brad just said, I hope everyone noticed that when we talk about getting to the least expensive hydrogen, we're able to go directly to electrolytic hydrogen rather than using the carbon capture technique that is the subject of this talk. At this point, if you have renewable power purchase agreements in that $1 to $2 range per kilowatt hour, penny to 2 cent per kilowatt hour electricity, giving you 50 cent to $1 a kilogram hydrogen, then you're in much better shape than you would be with any of the numbers that Brad showed on the graph showing what the cost of hydrogen would be with steam methane reforming and carbon capture. The trick is how you refine that target of $1 a kilogram. Does that $1 a kilogram mean generally available globally for $1 a kilogram? Or does it mean $1 a kilogram in certain places? Well, the answer to $1 a kilogram in certain places is yes, absolutely, we will be there by 2030. Generally available globally requires a great deal of international cooperation, near perfect coordination among companies and governments in public-private partnerships, and an enormous increase in the number of available electrolyzers. In a previous session, I think Brad noted something like a 400% increase in the number of electrolyzers would have to be made and put into service in the right places between now and 2030. So the answer is generally available globally. It's conceivable, but if I were putting a percentage likelihood on it, I would put it in the 20 to 30% range. So anyway, that's my major comment about that. The secondary comment is that because of the additional costs, because of transportation, compression, not to mention taxation, it's conceivable that hydrogen produced with steam methane reforming and carbon capture could result in a retail price of the hydrogen that's lower than electrolysis hydrogen, simply because the steam methane reforming plant is located closer to the market and closer to the end user. So it becomes very user specific on what the retail price looks like.
Yeah, there's a natural gas to liquid fuel plant that was built by the Department of Energy, I think in 1989 or something, for a very large price. I think it was $1.2 billion in North Dakota. And that plant has been, I think, inoperable for some number of years. And somebody picked it up for a song, but they're going to convert it to produce hydrogen. And they're going to use a blue hydrogen strategy in that particular case. And indeed, it's a landlocked location. There might be a market for the hydrogen that's near to them that can be serviced in any other means. So I think Rick's point about the geographic issue is key here. Any other questions today, Rick?
There's a very specific question, so we either know it or we don't. What is the pressure inside the CO2 pipelines that you mentioned?
Yeah, great question. I have no idea. The pipelines are designed around pressure. Doesn't matter what the gas is, and they can the characteristics of the gas will only determine how much gas you move at a certain pressure, and so CO2. That's a great question. It's probably like a natural gas transmission pipeline pressure, but that's probably easily understood. We'll explore that in the post presentation.
I see that we have hit the 1 o'clock hour, at least 1 o'clock Eastern time, and the remaining questions we'll answer and post along with the materials from the presentation in a few weeks, or maybe less than that.
Yeah, I think Rick, I think we can answer a few questions if people want to stay on the call. Somebody mentioned
go ahead.
An H2 project in Maine, and there's a company called Summit Gas in Maine, which is putting together a project to produce renewable natural gas. And one of the things that people are not aware of is that when you have a wastewater treatment plant, an anaerobic digester, or a landfill, they all produce what's called biogas, and that biogas has a mix of methane and CO2. The landfill, the microbes are producing the mixed gas. In wastewater treatment plants and in agricultural waste circumstances, you aggregate the bio waste into anaerobic digesters and produce the biogas. And that biogas typically has 55% methane, 45% CO2. And so all the anaerobic digester projects that are used to produce electricity through generators, they emit a fair amount of CO2. So the opportunity exists to take a anaerobic digester that takes in, say, manure from dairy farms, and to process that manure through an anaerobic digester, take the mixed gas biogas that comes out of that digester, separate out the CO2 and the natural gas and the methane, inject the methane into the natural gas pipeline as renewable natural gas, but then take CO2 and combine it with hydrogen from renewable sources through methanation to produce additional methane that then also is injected in the pipeline. And the process of methanation is well understood. Again, it's a nickel bed, and you use the mixed gas across that nickel bed in it's a catalyst, and you actually combine the hydrogen and the carbon to produce methane. You increase the methane yield of these projects by 70% by introducing hydrogen into the process. So it's an appropriate thing to do. It does require bringing together certain technologies and capabilities, but Summit Gas is pursuing this design in Maine, where they'll have 10 farms that aggregate the manure from cows, run it through a digester, use hydrogen to mix into the process to produce methane, and inject that methane in the pipeline as renewable natural gas.
I think the question, and there were a couple of comments following up, had to do with the Hydrogen Energy Center project that you mentioned in your introduction, which was the Chewonki project. And someone asked if that project is shut down. In fact, it is shut down. We opened it in 2006, and we were using and what at the time was really an alpha, not even a beta generation, but an alpha generation of an Avalance high pressure electrolyzer. And the Valence electrolyzer, when it ran, was terrific, but had some downtime. And because of that, because of some back and forth with the Valence, we eventually terminated the project. We were using Rely-On fuel cells. They worked fine, but we did have a problem with the electrolyzer. Someone asked, does the use of carbon capture appear in the, I'm sorry, nanotube manufacture? Does the use of carbon for nanotube manufacture appear in the numbers with respect to using the CO2 and the carbon that comes out of pyrolysis?
Yeah, I've seen some reference to the nature of the formation, but that is a potential use for the carbon, but it's a very small market, as you might imagine, relative to the amount of carbon that's being captured. Somebody asked what the energy efficiency is of using amines, I think, and all of that increase in the cost is really due to the energy. So it's energy intensive. You're running pumps and blowers and heating things up, and that's really where the money goes in those processes.
There's a comment, methane to green H2 question mark, that might need another color.
Yep. So if is that the run of the questions, Rick, do
I
you
think
think?
that's the run of the questions, unless there's, if somebody wants to unmute and chime in with a question that we've overlooked, please feel free to do that.
Excellent. Well, thank you everyone for this time together. And I appreciate your coming on board to participate. I do urge folks to sign up to be a member of our professional association, the Hydrogen Energy Center. We certainly are available to answer any questions or engage in any conversation regarding these matters, all things hydrogen. And so we appreciate your time and attention today. Rick, is that it for today?
I believe so.
Great. Thanks, everyone.
Thank you, Brad.